Test, test. Okay, so hi, my name is Victor, and I've been working for about a year at Odoo, and I'll be continuing the speech of Nicola about improving performance. But in my case, it's like when you have your bottleneck in the SQL query, usually the solution you find online is adding an index. But adding the index itself is not the hard problem. The hard problem is understanding why we add an index. So here you can scan a pad for your Q&A session in the end. If you have any questions, I'll be around answering in the best of my abilities. So, to index or not to index is usually the question we ask ourselves when we make a new field that's stored, so we know it's the database, that do we need one or we don't need one? Because we know that Postgres doesn't use the index always, but when is the case and why do we need them is an important question. So a little question, why do we care about performance? Because performance matters. Usually it converts to better sales, better conversion. You generate more revenue, you reduce operational costs because your database doesn't need to work as much to do what it needs to do. You have employees that are more productive because they can confirm that invoice faster. They can talk to the client, it be more responsive, reactive. It's also known that when you have a lead, if you respond and react to 20 minutes, 20 seconds, it's always more efficient. And essentially a good tool is one that doesn't get in the way. You don't want to do something and have to wait 20 seconds until it's confirmed, it's done, because it's annoying. And it's preventing you from doing what you need to do. So this talk is a bit theory heavy, because that's what's needed to understand about why do we need an index and how do we use them. So yes, nobody likes theory, but we need it. And the biggest problem in computer science in general can be reduced to this simple diagram. We have some data that's read from somewhere that needs to be transformed and processed, and then we output that data somewhere, we write it to disk, we write it on the network card, we send it to another server. In the end, it's just a sequence of this process, and the performance fix, let's say, is to reduce the time it takes to go through this whole pipe. So we read faster, we process faster, which is usually Python code or the query itself, and we output it faster, we write it somewhere. And how do we write data in your database? Because we are not using a text file, we use what we call a Postgres database, which is a relational database, which means everything is stored in tables. These tables have links to each other, which are called primary keys and foreign keys. We have constraints and stuff. It's a database that's called ACID, so it's an acronym for Atomicity, Consistency, Installation, and Durability. In short, atomic means that you have transaction, and when you have a sequence of steps that are done in one transaction, when it's committed, you know that all of them have executed successfully. You don't have the first step that passed, the second step made an error, and then you have an inconsistent state. Consistency, this is all basically the triggers and the constraints that when you say, if I delete said record in said table, another table needs to be set to null, deleted, to be consistent. For example, you cannot have an attachment that doesn't point to a binary file if the binary file is deleted. Isolations is what Nicola mentioned about the repeatability isolation level, is that multiple transactions do not influence each other. It shouldn't be correct to have you read something and have it modified midway by another process, change the information reading because it's inconsistent data. Durability means that when something is committed, it's written on disk in such a way that if the database catches on fire and stops working, your data is there and it's safe and it can be retrieved. Postgresql is also a mature software. It's been years, like since the 80s in the work. It's feature rich, it has a lot of extensions, it's open source, just like Odoo, and there's an active community because it's actually used. It's not a dead software. So we store data in tables, and here's an example. We have our fields, ID, name, and colors with 3 rows, the names and colors. A row in PostgreSQL is called a tuple, because one of the principles that Postgres uses to be able to roll back, for example, a transaction, is that we have tuples and we have copies of tuples that are created when we insert data or delete data. So nothing is really deleted until the vacuum process goes on. These tuples are stored in blocks and in pages. So in the documentation of Postgresql, you will see the word pages, but this is the most overloaded terms in computer science in general. This is not the same pages that is used by your operating system when it needs, which is using for like, I'm reading a part of your disk and I put it in RAM. This is the pages from Postgresql, and it basically means it's a block of data. So in that talk, we'll use them interdependently. Postgresql is a system that we use SQL to speak to. SQL is a declarative language. In a declarative language, you specify what you're doing, not how you're doing. In Python, you say, I want this, and then this, and this, then that. In the SQL, you just specify, here is what I want, and what condition it should satisfy. But you let Postgresql to decide what to do about it. So how does it process? Because in the end, it's code that needs to be executed. So we have these 5 steps, which is like the first 2 steps, the parser analyzer, which is meaning just we parse the query, we construct a syntax tree, and we analyze that, hey, the SQL query we wrote is actually correct. Then we have a rewriter, which is basically a glorified pattern matching substitution, which is like taking part of the query and replacing them with other parts of queries and other constructs that are more efficient and better optimized. Then we have the planner, which is usually our point of interest, which is like Postgresql. We decide how many, in which way it will work on to produce the code that needs to be executed to execute what you specified in your query. And then you have the executor, which takes the plan and executes node by node what the planner said. Okay, you do this, you do that, you do this, and the executor in the end gives you the result. So when we care about performance, we want to pay attention to the plan that's used, because this is what determines if the query is fast or if it's not. It's usually there, you understand if you need to add an index or not. So how does it work when you make a query? So we have our example with the table, and we have a simple query that's like, give me the name of the people that like the color blue. So Postgresql, what you do first is fetch the pages where the table exists, because it needs to read it from disk. So that has a cost. Then, line by line, we check. First line, is the color blue? No. Then the next one, the color is blue? Yes. The next one, the color is not blue. We discard it. And in the end, we select the name of the rows that give us the correct answer. That's what's usually done. But where's the problem? What happens when we have almost 100 million lines with everyone likes different colors and not bunch not? First thing, we fetch more pages because the table is larger, which has a cost. Reading from disk is not free. We do a sequential scan, and we filter out just to give one row, the name is Bob. This is slow, of course. So what do? We can ask Postgresql to give us the plan that he used. We write a keyword, explain before the query, and it gives you a result of the style. Here we go. We did a sequential scan on the table people, and we filter out everything based on the color blue. And we can see on the right the costs. The cost is what Postgres uses when it tries to estimate, okay, how much time, what does it cost, basically, to do that step. And basically, this is the basic and the default way that Postgresql accesses data on the disk. It's always going to do a sequential scan, worst case scenario. The explain keyword, that query will just do the whole process we saw before the executor. So the query is not executed. It gives you only the plan. You can add additional keywords around the explain. The most common is just explain analyze. Analyze will execute the query after that and give you additional data like execution time, what kind of thread it has. Costs give you, for example, additional information about the cost that was used. Buffers give you like input, output. So basically what's written on disk, what's read from cache. Verbose give you more information. And when you have a really big query and a really big plan, you can use tools like explain.dalibo.com, which takes the plan that's a text file that's maybe hard to parse, and it gives you a nice graph that's visualized with, hey, this node is red, maybe pay attention to this one. A particular important point to pay attention is that when you use analyze with a query that modifies data, it runs a query. So if you want to test, if you're deleting something that's slow and you don't put it in a transaction and roll back it, it's gone. If you delete an attachment to test because deletion is slow, if you analyze it, it's going to execute it. So if it's not in transaction so you can roll back it, you lose the data. In the end, we have a plan. We saw it's a sequential scan. What can we do about it? And here comes the big question of indices. What's an index? It's just a data source that lives next to the table. And it has a key. In our case, we use the color. Postgresql, we do the same query and request give me everything that likes the color blue. The index returns the tuple IDs, so the IDs to the row that are necessary to be fetched from the table. And it can shortcut and not need to read the whole table to know, hey, which are the row that likes blue. This is an alternative data retrieval method, which is called an index scan. It's because we first inquire the index about which tuple to go, and then we go to the table and we fetch only the rows that we need. Indexes can be customized in a different variants of way. We have unique indexes, compound indexes with multiple keys. You can be conditionals, which are called partial indexes. Covering indexes are like an interesting point, especially for PostgreSQL, because it's a bit specific to them. You have column transformation, which is like a big trap, especially in Odoo, because if you don't put the correct functions for your indexes, they might not be used, because Odoo uses a lot of functions internally, the ORM, to create efficient queries. And then you have also indexes that adapt to specific operators in your query, which is like the type of the index. So, in short, the unique index, what is it? It's an index that enforces a constraint of uniqueness. So, basically, every value of the index is guaranteed to be unique and not be repeated. This means that by default, because this is how PostgreSQL enforces on a unique constraint, is that on every primary key, because they are unique by definition, there is an index on it. So you don't need to index your ID field, for example, because there's already an index. This is also the same for like the unique constraints. If you put an unique constraint, even if it's not named create index, it means that Postgres will put an index on it to enforce the uniqueness. So you don't need to index a field that already has a unique constraint. Compound indexes are indexes that matches for where queries where you have multiple columns and multiple conditions. They are more specific. They are usually faster because you scan usually, if you have an index that's too general, if you give, and then you have a query that needs to fetch, let's say, 20% of the data, you still need to scan 20% of the table. But if you have a more elaborate index that matches more specifically to the query itself, and that index can say, hey, you need to fetch only 5% of the table, turns out it will be faster because you scan less data. The order is actually important because compound indexes are not used for every type of combinations. For example, if you have a combination only on, you have a compound index on all the fields and you use, for example, only the last one, the index will not be used because Postgres cannot know, okay, I have this compound index, you request me only the field Z, but I cannot use it. So here I've set up the order that usually Postgres can deal with because it's no, okay, I have an index that's compound and you request me the second and first and the first and second field. I can deal with it. The third field, I will give you all the rest that's needed. A partial index, it's an index when you put just an additional condition on it. So it will not keep all the rows that satisfy the key, but only those that you specify based on the condition. And the main advantage of it is that you reduce the size of the index, because on a production database, sometimes you're constrained by space, and you need to save out some space. Also, because the index itself is smaller, this means it's read faster from disk, which means it's also a bit faster. But the problem is that it's less generic, so it might not be used for as many queries as you anticipated. And an additional interesting point is that your condition doesn't need to depend on the key itself. It can depend on another field. For example, in our case before, we could put, give me the key, an index on the keys blue, but exclude everyone that's named Bob. In our case, in that index, we will not have rows that have the name Bob. covering indexes are a way to just stuff more data in the index. And you can use it for the include keyword. And this is an interesting point because it makes stuff faster for basis, but this is a PostgreSQL specific like superpower because other databases don't have such options or have an alternative one. And that's what we call an index-only scan. So we have the same scenario with the largest table, and we have the index, but we included the name inside the index. When we request the information, not only do we have the tuple IDs, but we get a copy of the value of the key and what is included in them. So PostgreSQL already has the color and the name, so it can satisfy whatever the query was. In our case, we requested the name of all the people that liked blue, but we already have them. We don't need to go to the table to request that information. And this is what we call an index-only scan, and it's the fastest method we can retrieve data from disk. And functional indexes. So you can put functions on the data that's being input into the index before it's inserted in it. In our case, we have, for example, lower color. Lower takes a string and basically put them in small case. So in our case, like we match multiple variants of mixed case of the word blue, for example. The important point is that queries that do not match the index with the function will not be used, and inversely, in queries we have a function, will not use indexes that do not have the function. So they need to be in synchronization with each other. This is usually an issue when we have, because the ORM inserts functions in some places, in some conditions, and when you add an index manually in the table, people wonder why they do not work. For example, a good example is like an accent, which I will cover a bit later. And another sign point is that the functions need to be immutable. PostgreSQL needs to know that when you give him a value, the result will always be the same. So the type of indexes, there are a bunch of them, and you have extensions to add even more. You have B-tree, the B stands for either binary or balanced, nobody knows. Trigram is like a type of a general inverted index. You have hash index, a block range, general inverse tree, a space partitioned index, which is like really practical for like map data, and you have Bloom index, which is like the last cry of technology. So the B-tree index, with PostgreSQL, it's a modified version. You can think of it as a balanced tree. The big advantage is that it's a bit less faster on reads. It's not as optimal as possible, but it's more optimal on write. Oops, sorry. So, and also the B-tree is a version which is called like the B plus tree, which is, as you can see, the linked list between the leaf nodes. So this is the default indexing method in PostgreSQL, and it supports many operators like lesser, great, equal, not null, and it checks basically you have like the root node, which is like, okay, everything on the left is usually values that are lower than what I'm looking for. Everything on the right is bigger than what I am currently. And an interesting point is that if we need a query that scans, for example, I don't know, a date, and the date is said, okay, give me all the values between the date of the 1st of September to the end of the year. What we just need is that, like, find the smallest part, find the smallest date, and then just go through the linked list on the leaf nodes without having to go back in the tree and start searching again. This is actually a really interesting implementation detail of PostgreSQL. This is the index that's used for the primary keys and the unique constraints. A generalized inverted index, also known as the trigram index, is what you want to use when you want to make your I like and like faster. So in short, you have a string and you cut it in small sections of 3 letters. So we have, as the example showed, like first blank blank A, blank AB, and these small trigrams, 3 for 3, are put in some sort of container that's easily searched by. This is useful for text and JSON data, and it's mostly for text searching, but also it implicitly gives you a probabilistic similarity ranking, because for each bucket you have all the rows that matches that trigram, but you may have multiple rows that match said trigram. So if, for example, you have a search on ABCDF, you will have this trigram generated, and you hit multiple buckets, and basically the buckets, the sum of the rows inside these buckets will give you the probability that it's used. For it, you need an extension, which is like once per database, you can use create an extension PG trigram, and then you can index it with using gin, column key, and then trigram operations, which is like for tell Postgresql, hey, use it for like and I like also. The hash index is a bit more niche, so it's the same. It's basically a hash table. You have a string, you pass it through a hashing function. In our case, hash3. It's a non-cryptographic function. The goal of it is just to have a nice distribution of the data for the buckets. The advantages is that you have a constant speed lookup regardless of the size of the table. It's always just the same. You just hash the value and you go to the bucket. It has a low overhead because it doesn't take that much memory. But the constraint is that it's only used for equality and existence checks. Existence check is like, is it new or not? In our case, for Odoo, its practical use is for selection fields because you always has a constant number of keys that are used for selection fields, and you always check, does it field is equal to something in a selection, or is it in something of multiple keys of the selection? In Odoo, we index is actually pretty trivial. We just add an attribute on the definition of the field index true. Index true is actually by default the string b3, which is mean we create a b3 index on it. We can add a b3 not null, which is like a partial index on the b3 that doesn't contain any value that have none. You can add trigram indexes, which creates a trigram index on the character fields. Useful. Also, it's on by default. It's good to put them on text field only. Sorry. And false is like the default value. Don't put an index on it. It can be interesting to put index equal default explicitly to tell the other programmers, hey, I've tried to index it, it didn't work. It's not needed here because an index will not be used for data that not have a high selectivity, which I will come to later. We have also an example of the Python definition for a constraint of, this is an SQL constraint, and this is basically creating a unique index on it. And you can specify more complex indexes in the init method. You can add if not exists, which basically we guarantee that when we upgrade the module and we run the init method a second time, by default, Postgresql will throw you an error if the index already exists, but if it not exists, we will not run the code. A special case for the ORM is like since Odoo 16, the trigram indexes translated fields or JSON fields. And JSON fields, the ORM will inject a function, which is called JSONB path query array, which means we put only the content of the translated field inside the index. We don't put the key of the language inside the index. It doesn't make sense. We don't search on NUS fr_fr on the locale when we do our like queries. And then the story about an accent. An accent is a function in Postgresql to remove all the accents and specific symbols. Basically, it's like a table. If I see that symbol, it should be translated to another symbol. That's a nice way to search, for example, a name without typing the accents. And Odoo, you can run it with the Odoo bin process with an accent. And the issue is that when you install a module, the index are created only at the installation of the module. So this means that if you run Odoo bin process with an accent, you install some module, the index that are created will have the index, an accent function in the index definition. But if then later on you restart your process without an accent, suddenly you don't have indexes that support them because your indexes have the unaccent function. As we said earlier, that queries that have no unaccent cannot use indexes that have an unaccent function used for it. Also, an accent by default is a mutable function because it depends on some Postgres configuration, because the mapping of what letter to what to map can be configured by the end user in a configuration file. But in the case of running Odoo, because all query pass by the same PostgreSQL user, we have the same config, so we can force it, which is technically correct. We can do outer function an accent immutable and say, hey, an accent is actually immutable, and then we can use it for an index. So we learned a bunch of stuff about indices, and they are awesome, right? We can index all the fields, obviously, and for all possible queries, we add everywhere. That's not the solution for everything. There's nothing free in this life, and there's a cost. If you add an index, the reads are faster, but these indexes need to be in sync with the data in the table. This means that when we write something to the table, we need to update the keys inside this index. And that has a cost. This is not free. For example, the tree needs to be updated. The trigram indexes, you need to split again, put them in the bucket. So it's also data. So this data needs to live somewhere and lives on disk. So it takes additional size. If you have a limit of disk size, maybe adding too many indexes, especially the trigram index, which is like really big when you index incorrect fields. Like for example, a description of a task with really long paragraphs inside for millions of tasks, it can get quite a few gigabytes that you may not have to do. And the most odd problem is that people face is that I have an index on this field and Postgres doesn't use it. Why? The answer is that the selectivity is important. So here's a little graph that shows basically on your x-axis you have the number of rows that needs to be fetched from the table, and on the vertical axis you have the costs of it. We can see in red the sequential scan is like constant because you read always the whole table. You have the index scan, and as you can see we have an intersection point. The index scan is basically not always faster than a sequential scan in Postgres terms, because you need first to fetch the pages from the index, run the index, get the result, fetch the table data, and then read the necessary rows inside the table. So there's a point. This is why we speak about selectivity, and we say the index is only used for a small percentage of the rows in the table, because if you need to read 90% of the table, there's no point in going through an index. You can just scan the table, it will be faster. This is why usually we see indexes that are unused. And then you have the special case of the index-only scan. Because the data is in the index, it's always faster to just go straight to the index and get the data that we need. So, a bit about hotspot optimization, which is like a term for saying this is the easiest process you can follow to optimize your code when you face some performance issues. And there are two rules for it. You never guess, you always measure, because we are not computers and we don't know, we cannot make assumptions about what's going to be faster in some imaginary universe. We have profiling tools that we use to understand where's the bottleneck, because we may think that the bottleneck is one place, but it's actually another. And then the second rule is that when in doubt, refer to rule 1. There's no other rule, it's just profile. And here's like a schematic representation of what do we do. We profile the code and we find a bottleneck. It's usually when you run the Odoo profiler, you will find, if it's an SQL bottleneck, you'll find a long row with the SQL query in it. You know that this query is slow. So you look at it and you try to make hypotheses about what do we do to improve its performance. Maybe we add an index, maybe we rewrite the query for it to be faster. We test the hypothesis, because just adding an index because you saw that you have a sequential scan with high filter rate doesn't mean that maybe the index will not be used, or maybe Postgres will choose another plan that's maybe less optimized than what you thought it would be. And then you profile again, you see the result. If the results are good, you're done. If it's not, you go again, you try something else. And the juicy bits, the quick tips. When you look for issues, you look for a sequential scan that filters out a lot of data. If you see a sequential scan that scans 99% of data, maybe you add an index on it, and that's it. That's usually a good solution. Compound indexes versus multiple indexes is a choice you make. When you have a compound index, this index is like really specific to a type of where clause. But if you have multiple indexes, they might be used. They are more generic because they might fill in issues for other queries. And for example, Postgresql, in that case, it will scan both indexes, get the tuple IDs, do a bitmap of which blocks it needs to fetch from disk to go and read the data. If you have where and something else, it will be a bitmap and. If it's where or something else, it would do a bitmap or between those two results. It will get the list of blocks that it needs to scan. It will scan only those blocks and read those only. That's how multiple indexes or single keys are used together for a more complex condition. you can exploit the order of B-tree index because it's an order tree. If you need to scan, for example, let's say the first 80 users that follow these orders, if you have an index that matches the order of the request, it can use the index to go and start to scan the index from A to B only for the first 80 users. And also, Postgresql can scan the index in reverse. So we sometimes find that are like, it's called reverse scan index, which is like if you give me the last, I don't know, like the last 100 invoice lines, and you have an index on the date of the invoice lines, it can do and hit the index in reverse. Partial indexes on sparse relationships. If you have many-to-ones usually that are linked to another model, and that model is not always linked to a model. For example, you have task and you have helpdesk tickets. Not every helpdesk ticket has a task associated with it. So if you want to have an index that points from the task to the helpdesk ticket, it doesn't make sense to include tasks that are new inside. So you put a partial index, a B-tree not new, on that many-to-one to speed up that search. Basically, it's free space because you will never look for a task that doesn't exist. Unique and indexes, we already covered them. Translate through is to, when you create the ORM, when you have a field that translates through, and if you have an accent on top of it, make sure that you use the functions that are defined. The function before with the JSONB data array, and an accent that comes on top of it. So you have an accent, JSONB, and then the key. This is, you have an index that's correct, and it will be used with the ORM. Because if the ORM gives you a query with these two functions, and you do only, oh, I'm indexing a trigram index on this translated field, but you forgot that it's translated, it's never going to be used. The big difference between the ID of a model and the tuple ID. The tuple ID are not the same. So I made this mistake in the past, is that I assume that it's everywhere you see documentation, it's like the ID is in the index. That's what's used. But the ID is not the same. So if you, for example, I request the ID of set row in the table. That matches some condition. The index will give you the tuple ID, but it doesn't know the ID. It's not the same thing. So we need to go and scan the table. OK, is this a tuple ID 10? Give me the ID of this row. Maybe the ID is 4. And it gives you back. So you have an index scan. But if you have the ID inside the index, either as a last key in a compound index or in include, you will do on the index only scan because you will not need to fetch the table. An accent is a function. We should not forget about it. And that if we use different configuration of Odoo when we launch it and we decide later on, yeah, I will use or not use an accent, update the index accordingly. So you can actually use them. Because indexes are only created when the module is first installed. Index on Boolean fields and selection fields are sometimes useless. Because Boolean, it depends on the selectivity. If you have 90% of the data is false and the other 10% is true, if you put an index on a Boolean field, this index will only be used if you search for the true values, not the 90% of false value. Because of the selectivity, it's faster to read the whole table. So it's usually more interesting to put a partial index. Hey, I index this Boolean field, but only for the true value. Basically, put the condition only for those that the selectivity is small, when you have less data in it. The same for the selection fields. If, for example, you have a long-running business with sale orders, and you want to index on all the draft sale order for whatever business reason you need, if you put a generic index on it, you have an index that's not used for the done indexes, the done sale orders, the maybe cancelled one. So you can put a condition, again, a partial index in the init function to remove this data that's never going to be hit by the index scan. Not all nested loops are equal. So the nested loops is like a type of join. This is the default join in Postgresql. When you have multiple tables, try to join them. And it's a nested loop. It's like 2 fors. So basically, for each row in one table, I match the fields of the other tables. This is usually the default one and also the slowest one. The thing is, like, if we think like a database and we follow the process, okay, I take the first row of the first table and I go through all the other rows of the second table. Then I go to the second row and I go again, all again. So as you can see, we are doing a sequential scan. We can put an index on the second table so that when do a nested join, it will still do a nested join, but this one is faster and it's not written in the planner. You will not see. The only difference you will see is like it's faster to execute. because what it will do is like we go for the first row, hit the index, and know which row to join. So it might be an interesting optimization point in the case when PostgreSQL cannot use another merge type, which is like merge join or hash joins. And then you have the issue of cascade triggers. When you see a query, that's usually the case for like deletes, you have a field that you said, okay, if I delete the other guy and I want to be set to null, or just delete myself also. If we delete the other model, the other row, the other record, we need to go to the original table, scan it to find, okay, which row do I need to edit to match the constraint that's been set. And PostgreSQL, you can add an index on the foreign key on that table that we know, okay, when we delete the binary field, I need to go to the attachment. I have the ID of the attachment I want. I can hit the index and know which row I need to update the constraint. That's also something that's not shown in the planner. It's only understandable when you see that the cascade trigger takes less time. So this is maybe a hidden way to optimize deletes and updates also, because updates needs to be to maybe update the information. And that's it. Hope you liked it. If you have any questions, I'll be around, and I will answer to the best of my abilities. Yeah. So the first question is, does PostgreSQL decide if it uses an index-only scan, or do we need to do something? No, it's automatic. PostgreSQL, we choose, if it can use an index-only scan, it usually will use it. As a plan, basically it has multiple options to select, okay, I can do this part of execute the query, this one and this one. It will accumulate the costs, and these costs will basically we choose the less one. And usually the index scan only, because we saw that it doesn't cost much, will probably be preferred, but there's no settings to do. You just, if there's an index for it, it will use it. Working directly in PostgreSQL, sometimes you don't have the choice if you don't have access to the code, but only to the terminal. It might be interesting to put an index. Also, sometimes indexes are forgotten because not everyone is aware of like the implications that they are needed for. And so you may need to add an index after it. And also, for example, adding studio fields will change the query, how they work, and sometimes the indexes that are put in standard code are not going to be used, and you may need to add the studio fields inside your index, either as a compound index or as another index that can be used in multiple indexes, so your query gets faster. Okay, so for stored procedures, we don't use them in Odoo in general. They have their own implication. It's running a function, a custom function, so this code needs to be parsed, to be interpreted, and to be run. I cannot say more about it. I'm not super familiar with them yet. So maybe you can ask Nicolas. He may have a few words more on the subject. By default in Odoo, you cannot define compound indexes. When you put index true for many to one, it's going to be a simple index. The advantage of a compound index is when you have really elaborate write condition. For example, the company and active usually are keys that are added to other indexes to speed up some lookups. Yes, indexes, as far as I know, I may be mistaken, but are exported when you export your database, because it's part of the definition. If you decide to write a unique index, it's going to be there because it's part of the constraint. Yes, if you have two fields with index true, both indexes are going to be created. That's not a problem usually. For write operations, it's mostly look for the cascade, but there's nothing more much that can be done. Indexes are mostly used for reads operation like select, and are used implicitly with the delete because of the cascades. But inserts themselves cannot be sped up a lot. The only sped up you do is not write a lot frequently. Write in batches as much as you can. And usually the ORM does a pretty good job at batching the requests. At the end of transaction, we write everything on the database at once. Just don't do a search and start writing if like explicitly with a query SQL. Indexes that are declared in Odoo are used by Postgresql. They are created on the database. They don't, like Odoo itself doesn't create a data structure specific to the indexes. It just does the query SQL at the module installation. So there's nothing to set up specifically on top of it. Reducing concurrency is mostly a question of not having writes and in at the same time as much as possible. By default, for now, we have repeatable reads, so we retry the query later on. If you want, you can do some customizations on top of it. For example, you're having a queue system, like the requests are put in a queue and the queue is processed one by one. That's an option, which is basically a messaging system. But there's nothing much that can be done with indexes to improve concurrency updates. It's just try not to spam the database with writes, usually it's writes, on the same record at the same time. You can specify, for example, on like insert on conflict and do something about it. Like, for example, skip the row or just do nothing. That will resolve the concurrency because you specifically said how to resolve the problem. Odoo, by default, if you have a conflict, we just retry later on. The idea of managing indexes in Odoo and managing indexes manually is that in Odoo it will be easier to manage because you don't really think about it and it's part of the design. It's when during the design phase of deciding, okay, which field is a many-to-one stored or like a compute and how you organize your models with your foreign keys. That's usually you think of, okay, this model is going to grow rapidly. For example, you have account move line, which usually grows more rapidly than account move that are linked to it. So at that time, it might be interesting to put an index on the account move line on the account move. Because you have more account move line, it's going to grow rapidly. But for example, for the model unit of measures, it doesn't make a lot of sense to put indexes on it because it's not a model that's going to grow exponentially. Like, how many ways do you have to count liters, milliliters, kilograms? You have what, top 50 rows that are distinct? So there's no point in indexing any of the fields on the URM because it's always going to be faster to scan the whole table. It's just 50 rows. But if you have a table that's going to grow exponentially, for example, you keep analytic records of something that happens, this is something that's going to be written everlastingly. It's going to take millions of rows. Then in that case, it's a part of the design decision to, okay, what type of index I put, what do I need, and also, do I have the space to index all the fields I need, or is there some compromise that I can do? Can I not index a field because it's taking too much space? For example, we had an issue on our own database of people searching, like they wrote the design decision of, I want to be able to search on the Kanban view of the project task to search in the description of the tasks. So we have a really big project that's used for our ticketing system that has over like 200K tasks and tickets. And people put stack traces, images, and stuff in the description. If you want to do an I like on the description, we need to put a trigram index on it. But this trigram index grew like to the 60 gigabytes of size. Do we want to waste 60 gigabytes of size just to have an index? And also, these 60 gigabytes need to be read from disk into RAM. So reading 60 gigabytes is not free, depending on your server and how you, if you correctly set up PostgreSQL to tune your database for the hardware you're using. Because if you have spinning disk, it's not the same as having an SSD, as having an NVMe drive, as having another disk on a network. If you need to do a network request for 60 gigabytes and that network server is on the other side of the globe, it's a hypothetical saying, like nobody's going to put your database not close to the Python server, but if it's the case, it takes time. So this is decision that you need to take when you design your system. But in general, the good idea is that you choose at the design time you index in Python. You decide, okay, this is going to be bit3 not new, and stuff of so on. But when you want to fix issues that are like during production, usually it's faster to go add the index, see the result. Does it work? Yes. Take note later on, and maybe a week later, 2 weeks later, make a patch for your custom code or submit a PR request to Odoo, and we'll fix it. Because usually when we work and we design, we cannot always foresee the use case that a client may have that may be out of standard, that maybe needed an index in such case. I'm not an upgrade expert, but when it comes to upgrading indexes, in general, like they are leftovers. So it might be interesting to, when you upgrade your database, look for the indexes of old fields that do not exist anymore because they will not be used. You can search around for the Postgres documentation. There's like a really elaborate query that gives you the hit scans of indexes. This is actually interesting because it gives you the information of, hey, at this time period, the index has been hit 1,000,000 times. If you take the same query a month later with the same result, and you see that it's been used still 1,000,000th time, this means that during that time period it was never used. If it's never used, you can delete it safely. Also, deleted fields, I mean, they don't exist. You cannot do the ORM cannot do a query on a field that it does not exist anymore. So there's no point of having an index there. You can freely remove it. When it comes to load balancing and scaling, this is more like an infrastructure question. When it comes to indexing, it doesn't like, the index is like bare database, so it doesn't really impact your decision of what kind of infrastructure you're putting. Sometimes you have connection pools, which is usually one thing that's done. In the front end, basically, connections are not created every time a request is made. You have an object that contains the connections that are kept open, and when a request comes in, you just give the connection so it can do the query without initiating the TCP handshake and the protocol verbosity of transmitting data. Okay, we set up a connection, then we can run the query. That's usually something that's done. But for infrastructure questions, feel free to go to the backend, find someone either for the Odoo SH team, which is like our cloud platform, or the internal team also, because we manage our own platform, or the infrastructure team, which manages the SaaS and the database that we have. When it comes to choosing between, do I use the ORM or do I make a custom SQL query, usually prefer over everything the ORM first, because it's easier to maintain, everybody can read it. It's usually also like really practical to modify, and you have the ER rules that usually people forget to use when they use queries. Also, it will be consistent with the cache, because when you do an SQL query, you bypass basically everything in the ORM, which means that fields and data you read from a query is not put in the cache. So if you have, for example, let's say you have a transaction that's going on, you do some Python modification, you don't flush the cache. This means the information in the cache is not put on disk. When you do your query, the information you'll have back is not the correct information. It's been the old data that's not updated with the cache, so you have inconsistency there. Sometimes you may find bugs. So if you have a query, always flush at least the record that's associated with the tables you're touching in the query. Also, when you update something, make sure that, hey, if the query changed, maybe update which record set you're flushing. People forget about them, you have inconsistency, and you have odd to reproduce bugs, because it's really hard to reproduce the issue, because usually it's like in odd cases in that time, because I wrote something, it's not updated. For profiling, I personally use the Odoo profiler, which is like pretty for my needs. You run it, you have usually the query at the bottom end. as a long, usually if it's the bottleneck, it's going to be long, you're going to see it. It's not possible to miss it. And you have also the query that was run with the values that are run. Then you can take that query, there's like a bit of string beforehand that's like a resume, a recap of the query, but the rest is like the full query. You edit it a bit, you run it on Postgresql with the explain and analyze, you have the plan, you plot the plan in explain Dalibo if it's really big, if you cannot parse it like by eye because it's text and it's like 200k lines long, you're not going to read 250k line long text file. And usually you look for like, in my case, in general, like I look for like sex scans that have a high filter rate, or I look also, for example, like there's a big difference between queries that be optimized with indexes and sometimes queries that cannot be optimized with indexes. Usually this is the distinction between what we call like OLTP or transactional queries and analytical queries. Transactional queries are defined as short query because you don't touch a lot of data when you need to do something. When you read something like, I'm going to read the currency of set voice in voice line, you're not touching a lot of rows to execute the information, to execute whatever you need to fetch. But analytical queries, usually when you want to do business decision on some time period, you're taking the averages of whatever you sold during the time period of 1 year. Basically, it's accounting reporting. And when you do reporting, this query cannot be optimized with an index because you're reading a lot of rows of the tables. So in that case, usually you want to edit the query in such a way that first you filter as much data as possible before joins, because joins are expensive. After you've optimized that, you can maybe change the group bias. Maybe if I try to switch the group bias in such a way that you work with less data. The whole point of the first slide with the fundamental theory of like computer theory where you have data, process data, is like work with less data as much as possible, do as less as possible as processing. Like for example, Python side, there's no point in having an elaborate read group, then you put in a dictionary, that dictionary is put in a list, you do some manipulation, then you put in a table for. Try to be as parsimonious as possible, do less stuff. The less stuff you do, the faster your code will run because you have less to do. And then this information needs to be written somewhere. If you write something, the less you have, the faster it is. I think I went over most of the questions. If you have other questions, feel free to hit me up. I will be somewhere around the floor lobby, and I hope you enjoyed it and I didn't bore you too much. It was really theoretical. I know it's heavy, but that's the information you need to know to know, okay, here putting an index is a smart thing or not, because just indexing everything, there's no point. But you will find some people that say, okay, the pragmatical way is index all the fields, check 1 month later which index are not used, and then remove the indexes that are not used. But maybe it's not the necessary step to take.